All right. The thumping of fun is over. Pavlovian, you will cringe at this sound later in the semester because it means all your fun is done, and I have to talk again. How obnoxious I am. Okay, so first things first, important business first, which is the best sports-themed movie. You have discussed this with your peers. You have come to consensus. What is the answer?
Waterboy.
Waterboy. Okay, Waterboy. That's definitely wrong. I mean, that's okay. That's okay. Yeah. What? Sandlot. Oh, see, I think I'm too old for that. So that's wrong. Yeah. Caddyshack. Now he's like, you're old. Maybe I'll say Caddyshack. I'm actually too young for Caddyshack, so that's wrong. Yeah. Dodgeball. Oh. These are all okay. I mean, I'll say that you all have okay taste. Okay. Yeah. Miracle. I like, I was a kid watching the actual Miracle on Ice, and it was honestly one of the highlights of my watching any sports. My kids asked me, why do I like watching sports instead of just doing sports, which is a whole different topic. I like doing sports too, but as I'm grow older, watching seems to be better. But yes, what year was the Miracle on Ice? 1980. So I was 9 years old. And the Olympics, if you don't know the story, were this amazing thing at that time, which was the U.S. had a bunch of amateurs who were in college from places like Wisconsin, actually, and Minnesota, because those are the only places that are cold enough to play hockey all year round, or most of the year, or half the year. And the amateurs who were 18 or 20, if you don't know the story, were playing against the Russian team, who were basically just a professional hockey team. And there was, of course, the Soviet Union at that time. And somehow, they won. And it's kind of a fun movie. So I saw the real thing, and the movie was pretty good. So this is okay. I won't cross off Miracle. This is pretty good. Yes? Air Bud. Okay, definitely not going to write that down. Is that about sports? Yeah, okay. Shaolin Soccer. That was pretty good. I saw that a long time. I don't remember it very well. I remember it being about soccer. Okay, we're going to take apparently 20 more suggestions. Yeah. Space Jam. Yeah, let's boo that. I'm going to write that down, but then ignore it. Definitely ignore that. Yes. Blaze of Glory. That was pretty funny. Yeah. These are all they're all just comedies, so let's get more serious. Yes. Remember the Titans. Very earnest. Okay. Pretty soon I'm going to have to give you the answer. These are all kind of wrong. Okay. Yeah, well, two more. Yeah. Yeah. Sorry? McFarlane. I don't even know what that is. Is this a sports movie? No one's going to write down a name. Don't give me a name of some movie that isn't a sports movie. That's embarrassing for me to write down. You've given like 6 already. So, Balls of Fury. Okay, I don't know. All right, so these are all wrong. So the answer, of course, and this will be on the exam. So I'll give you 2 choices, which you will probably groan at and not agree with. One is, of course, Rocky. How can you not say Rocky? Yes, of course. Original Rocky, not Rocky 2, not Rocky 3 with Clubber Lang, not Rocky 4 with Ivan Drago, not Rocky 5. Who's in Rocky 5? Has anybody seen Rocky? Who's seen Rocky? Oh, thank God. Okay. So that's one. And the other one, of course, is the original Karate Kid. Boo. Yes, this is a great movie. This is one of my favorite movies. All right. So what determines your favorite movie? It basically just determines how old you are, because it's a movie you saw when you were a kid and you thought that was a good thing. Anyway, those are 2 of my favorites. So I'm taking suggestions for other topics. We've now covered best sports-themed movie. You've given a bunch of wrong answers, and I've given you the right 2 answers. If you name one of those on the exam, you'll probably get half credit for the whole exam. So that guarantees you 50%. So that's great. If you say like Rocky, not Rocky original though, you'll be negative points. If you have ideas for future break topics, feel free to send me an email. We may or may not discuss them. Anyway, it's fun to hear. Okay, so unfortunately, We can't just talk about random pop culture. We will now segue back into just the last lecture of this evening. This does raise the topic of if we're going to do a discussion at the end of today, you might be optimistic. You might think, this is great news. Tomorrow there was supposed to be discussion. We're doing it today. That seems like a good thing. But what do we know in this class? It always gets worse. And what does that mean when you're doing discussion today? What are you doing tomorrow? Lecture. That's right. We're all learning that if today is a break, it means tomorrow we must suffer. So that's bad news. Bad news. Or if you really like hearing me talk, it's good news. So is it good news? Who knows? Good news. We do have class tomorrow. And think about it. We just have so few precious weeks together, right? We have 14 weeks. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Just 14 weeks already. And we're just here. That's bad? No, this is good news. We still have so many left together, okay? And then here, then this is when you have knowledge. So this is a really good place to be. You have knowledge there. What you have now, well, what's the opposite of knowledge? Lack of knowledge. You have a lack of knowledge. Or maybe you know all this stuff, in which case the class is really boring. So that's okay. Okay, so now what are we going to do? We are going to get back into it a little bit. We'll just do a little intro into virtual memory today. We won't get into the heavy-duty machinery. Virtual memory is a microcosm of this class because we'll start easy and it will get worse and worse and worse and worse until we build a fully realized virtual memory system that does all sorts of crazy stuff in order to provide this illusion to you that you have a large, essentially infinite or large, very finite but large virtual memory, that you have a large private address space. So we're going to start talking about that today. We'll just get an insight into how it works. This probably will be some kind of review for you. That's okay. It's okay that we review a few things so that you remember what you had learned in the past, maybe in 354 a little bit, and then we'll get into it in more depth. So, virtual memory. Well, we have our abstraction. We have the process. The process is our running program. It's pretty great. We can have as many of these as we want now. Not really. Someone was bringing this up during break, a running program. That's processes, I guess. So let's just make it a process. Our running program is our abstraction of our computer, right? It's like it lets us have a CPU, and of course it lets us have memory. We already saw how to virtualize CPU because we can stop and start running things. Now, if we run too many, the abstraction falls apart, right? If you run 1,000 processes or 10,000 processes, and they're all trying to use the CPU, you're not going to think this is this amazing abstraction, because the computer is going to seem to each process that it's running 1/10,000th the rate of the system. So there's some level at which you need to just go buy more computers to do the work that you're doing, right? This is what happens in data centers. What do they do in the Google data center of the world when they realize that they have 1 billion Gmail users? I mean, isn't it amazing? We live in a time where there's a service that you can have 1 billion users, like Facebook or whatever they claim they have at least. Or Gmail. Gmail has like 1 billion users. I don't know how active each of them are. And these services run on these very finite data centers, so people have to support thousands and thousands of machines. And at some point, you can't just say, well, we're going to fold all this workload onto 10 machines. You're going to have to buy thousands of machines, and when the user population grows, you have to buy more machines. There's no magic. The CPU, no matter how smart the OS is, at some point you run out of resource, which is, in this case, maybe the CPU, and you have to buy more. We're not solving that problem. So that's something that we didn't really talk about. How do you know when you have to have more machines to do things? Maybe we'll talk about the end of class, like end of the whole semester. Another aside that we didn't talk about before we get into this, we of course also could have on many systems we have multiple cores, right? Multi-cores are common. I have 4 cores on this thing, or 2 cores, 4 cores, and when you have a few cores on a system, the scheduler has more choices. It can run more than one thing at once. It turns out it's an even bigger challenge to build an effective multi-core scheduler, but there's a few things we need to know about concurrency, which is the second part of the course, before we can even talk about really how to build a multi-core scheduler. So we will defer that discussion. If you want, at the end, we have a little bit of slack. We can talk about something like a multiprocessor scheduler. We also didn't talk about how Linux does scheduling. We'll defer that for a later time too, probably with Project 2B. Linux doesn't use a multi-level feedback queue for various reasons, mostly because the guy who decided to write some scheduler for Linux was like, this is the scheduler I wrote, and it wasn't a multi-level feedback queue, and it's worked pretty well. It's called CFS. It's one of the main schedulers of Linux. So we'll talk all about that stuff later, Linux, CFS, multi-core, etc. later. What we're going to come back to now is we have this abstraction of a running program. We're virtualizing the CPU, but our process, well, you think of process state as we have registers that are changing all the time, and really that's what we were dealing with when we were talking about virtualizing the CPU. It's basically, I have my registers, my program counter, which is just telling me where I'm running. I have my general purpose registers, which are part of my program. And then if I need to virtualize the CPU, it means I'm saving those registers, putting them somewhere, say in memory, in the OS memory, and then restoring some other processes registers, and then running it. That's what virtualizing the CPU is. It's essentially swapping those register contents and switching between programs really quickly. A much bigger part of the state of a process is its memory state. And we know what lives in memory already. We think of it abstractly as, say, code and a heap and a stack. Hopefully that's all familiar to you, as the knowledgeable people who know essentially how a C program runs. And we call this memory of each program, we call it something. We'll call it its virtual address space. It's just a bunch of bytes that I can address that are part of my address space, and that each byte can be referred to by a name. That name is a number from 0 to the size of the address space, -1. So on a modern system, this might be a 32-bit address space, or even more modern, we might have an incredibly large 64-bit address space. But what you can see is our memory here is what we're trying to do for each process is we're trying to give it a large memory. These are essentially our goals. And a private, what you might think of as a protected memory. And, of course, we want to give it an efficient memory. What we're going to do in the development of our virtual memory system is essentially attack all those goals all at once and slowly build up towards doing that. Why do we want memory to be large? What's the primary reason for that? Yeah. No, I wouldn't say it's a trade-off, really. I mean, that could be something, but that's not a primary reason. It doesn't really let us run more processes because we actually maybe have to run less if we give everybody lots of memory, yeah.
So I don't have to wait every time I need
Could be that if an efficiency argument that if if I have a, but we're not giving you necessarily. So the argument is, hey, maybe you need a large memory because if you don't have one, then you have to, get something off a hard drive, and so it's slower. That's an efficiency argument. But I'm just giving you the abstraction of a very large memory. In fact, it might not be a very large memory. It might be a medium-sized memory. But why is the abstraction of having a very large memory important to me as a programmer? What happens if I don't have a very large memory that I can use? Yeah. Close. I think you're getting at it. So what happens if I just have like a small address space? Let's say somebody says you don't have a 32-bit address space, which is 4 gigabytes of addressable memory. Let's say you're building a linked list with lots of stuff in it, because who wouldn't want to put a lot of things in a linked list? And you're putting a lot of things in this linked list, but you have a small address space. So let's say your address space wasn't 32 bits or 4 gigabytes. It's more like 1K, like the first computers I programmed back in the Stone Age. TRS-80 Model 1, tiny address space. Had actually physical RAM on that machine. Oh, what a boring story. Was 16 kilobytes. It's 16 kilobytes of memory. And somehow I found it interesting. So why? Did you have an answer? Because you have to think at a lower level. I like how you're saying that. What do you have to think about? What do you have to think about if you have a tiny address space? When you're trying to just build a linked list and populate it, what's going to happen? Well, how do you refer to, like in the C program, how do you refer to each node of a linked list? What do you refer to it by? Like when someone says, what's the next node, what are you giving them? What's the actual way to refer to a node? A pointer. What is a pointer? An address. What does it mean for each? So if we have a linked list, that means each node has to have an address. And it has, of course, a size. So if we have each node has a size and an address, what happens if we run out of address space to our linked list? Segfault. I like the answer to this class, everything's going to be like, it's segfault. So that might be true. But what happens is, if we want to make it work, what we're going to do is we're going to start doing crazy things. We're going to say, well, okay, here's my address space, and yeah, I filled it up with this stupid linked list, and I don't know why I chose this data structure, but most of the time it works. And then suddenly my address space is full. It means I don't know what to do at this point. So what I'm going to do, and people used to do this, is they'd say, well, I have this much bigger disk over here, and what I'll do is I'll take part of this linked list and manually move it down to the disk and kind of make some space for myself, and then now I can add some new nodes to the linked list. But then if I have to access that other part, then I have to go back to the disk and bring things in. It becomes a headache, right? Moving things out of memory, in and out of your address space because you don't have enough virtual address space to refer to everything you need is a headache. It's a programmer ease of use problem. So by giving someone the illusion of a large memory, having a very large address space, think about how large a 64-bit address space is. It's unimaginably large. We're giving them basically a programming aid. It's ease of use. We don't worry about, do we have enough space in memory? Now, we might not have enough space, and we'll talk in physical memory, and we'll talk about how to deal with that. And we'll talk about whether that works as an abstraction anymore. But it's an interesting thing. All these things are for ease of use, right? The first thing the OS is doing is it allows you to run many programs at once, even though you have only one or a few CPUs. The other first thing it does is it allows you to pretend you have a very large virtual memory that's private to your process, even though you might not have that much physical memory. And that's because it lets you not worry about what's in memory. Can I fit everything right now? Ease of use. Never forget about ease of use. We're trying to do ease of use. But we want it to be protected. We certainly want it to be the case. Like, let's think about protection. We want it to be the case that you have a process 1 over here, and you have process 2 over here, and you have the OS itself with its own data structures, linked lists. Its own data structures here. We don't want process 1 to be able to read from process 2. We don't want process 1 to be able to read out from the kernel. In fact, one of the big problems with the meltdown bug, by the way, one of the people who discovered meltdown gave a talk here yesterday, interviewing for a faculty job here, and hopefully we'll hire this guy. I hope you're listening, guy. I liked you a lot. And what a cool thing that they discovered this flaw in processors that lets an untrusted user program essentially read all of the physical memory of a system. This is bad. That's a big, big problem for Intel. Now, it turns out the meltdown bug is a little bit easier to mitigate. The other bug they discovered, which we'll maybe talk about, it's very complicated, is called Spectre. And there are some mitigations that prevent, that help with it, but they're still unsure exactly, how many problems like this exist. So it's a very kind of fascinating time in security, and things that we thought were secure are now it's a little bit dubious, actually. So for now, we'll pretend those processor bugs don't exist. And what we will do is assume that the primitives that we're going to build up actually do provide this protection so that we can't read the OS from a process, and one process can't read from another's memory. And you can see all the reasons why you want that: privacy, et cetera, reliability. So we're going to build up a protected memory. And lastly, we're going to build an efficient memory. And what that relates to, efficiency relates to, is it brings us right back to where we were before, which was, remember, our general way of thinking about this is limited direct execution. The direct execution means, in memory terms, it means generally when I'm doing loads and stores or instruction fetches, the general ways that we access memory, I want the hardware to do it without OS involvement. I'm building an abstraction that the OS is fundamentally providing of a large private virtual memory, but I want the CPU to do most of the work. Most of the time when you're running instructions, when you're accessing memory, yes, we'll do a little bit of work, but it has to be in the hardware. If every time you did a load or store, you had to jump into the OS and say, hey, is this okay for you to do? The program would run 1,000 times slower. No one would want to use the abstraction that you've provided. Okay, so just a little intro into this. So what we're going to now talk about are simple techniques into, sorry, I'll leave this up here. So any questions about that? Make sense? All good? Maybe review. Okay. So the basic, what we're going to do is, as before, we're going to start with mechanisms. There will eventually be policies that we need to layer on top of these mechanisms, but the mechanisms are the hard part, so let us understand how to build them first. And the mechanisms, as before, are going to be a combination of hardware that we need and OS support. And yes, I will abbreviate hardware like this all the time, so if you don't know what HW is, that's hardware, software. Anyway, so we're going to look at OS support and, of course, hardware support in order to build this, which means on each CPU that we build, we are going to have system support, CPU support for abstraction of virtual memory. And we have to build that correctly in order to provide this kind of protection that we need, and efficient protection. So what does that mean? It means that, well, let's think about memory access a little bit. When do memory accesses occur? Well, I've already kind of answered that. Memory accesses occur essentially all the time because first we have instruction fetch. This is, again, the basis of our understanding of how to build computers, von Neumann machine. We have, in memory, we have instructions and data. And so we fetch an instruction in order to see what to do, and then we operate on data, maybe, right? Or maybe we operate on registers, which is kind of, not memory, but a form of fast memory. So we're doing these all the time. And then, of course, we might do explicit loads or stores. A load, of course, being, from memory into CPU. That's a load. And a store, of course, is from the CPU, from a register into memory. As you know from your basic understanding of how a computer works, the closer we get to the CPU, faster things are. So we want to generally bring the memory, the data that we need into the CPU and work on it for a while in registers and then store it back to memory later. It's going to turn out, as we talked about on the very first day of class, those so many weeks ago, that's a huge problem when you're writing concurrent programs. Just that notion of I'm taking something out of memory, working on it for a while, and then storing it back into memory when I'm done, some changed version of it. That's a huge problem if someone else, some other thread of computation is working on it at the same time. We have a kind of a problem there. We're going to address that problem again in the middle part of the course. And that's, for those of you looking forward beyond virtual memory, probably the most intellectually challenging part of this class will be really understanding concurrency and its fundamental problems and solutions. So we access memory all the time. And now we need to, in some way, interpose on these memory accesses. We want to be able to make sure that you can't just access any memory that you want. If you could just form an address and read from it or write to it, you could, of course, read OS memory or write OS memory or read or write other processes memory as well. So we need some way to interpose on that. Interpose. We need to get in the way somehow. But we need to do it efficiently. And so the general mechanism that we're going to do is something that's called address translation. Address translation is something that's happening so often, so frequently in modern systems that it's amazing how often it happens. But it's a very basic thing that's going to, and the way we should think about that conceptually, of course, is we have, say, a process 1 here. It has its address space here. And the illusion is that, I just have a private memory from 0 to whatever the max size of my memory is, minus 1, size minus 1. And I can refer to each byte. And just to be clear and re-emphasize things you already know, I'm always going to talk about a byte addressable memory. Now, some instructions might deal with multiple bytes. Like in some architectures, when you say do a load, you'll get 4 bytes because it's the size of an int or a word, we would call it, and we'll put those 4 bytes in a register. Or maybe I'll do 8 bytes, double word or something like that. Or a quad word, they'll have instructions that move 16 bytes or even 32 bytes. But fundamentally, modern systems are byte addressable, which means the smallest unit that we can generally interact with the memory is 1 byte at a time. What if we need to change 1 bit? We just need to change 1 bit in the middle of a byte. What would we do? Cry, scream in frustration. Who built this byte addressable memory? What a devious person. Or we would ask a friend. Yeah, that's a good answer. No, nobody said that. Sorry? You look up in Stack Overflow. I need to update a bit in this byte, in the memory's byte addressable. What do I do? Marked inappropriate. Should have learned in school. What do? I have this byte addressable memory. I have this byte, these 8 bits. What do I do? As somebody, all of you know probably, what do I do? Yeah. Coalesce, what does that mean? I mean, I know what coalesce means, if you're worried. He's like, that guy doesn't even know English. That's okay. They didn't hire me for my English skills. So actually, it remains a mystery why they hired me. So anyway, if we really want to see old stuff, I'll show you my job talk, which was given. There was a projector, and then you have these foils. You put them on there. It would use light to project onto the screen. So you kind of, when you were interviewing for jobs, you would carefully walk around with this box of your carefully prepared foils. And of course, if you lost them, you couldn't give a job talk and you couldn't get a job. So that's the old world. And then, of course, people invented the laptop. So that changed all of that. So what are we going to do? We want to just update this bit in here. So we have a CPU, a program. We have a byte addressable memory. What do? Write a program that updates that 1 bit. What does it do? Yeah. Yes. So any system, and you all probably just didn't want to say this, anytime you have a storage system of some kind, whether it's a memory, which is byte addressable, or a hard drive, what's the smallest unit of access on a hard drive? Who knows? No, much smaller. A sector, yes, it is a sector. Hard drives are sector addressable. How big is a sector? A quadrant, quantile. Okay, well, how big is it? Anybody know? Guess. People are saying 4. I don't know what unit that is. Anybody say 6? Do I have an 8? How big is a sector on a hard drive? Somebody knows. Who is a hard drive expert? Yes? 512 bytes. That is right. Okay, you win tonight's prize. 512 bytes. So that means disks have this problem even more so. If you want to update anything less than 512 bytes, you have to read the whole byte block, the whole sector in, modify the part you want to change, and write it back out. What does this mean if you're doing small updates in general? This is an aside, by the way. As I said, I will occasionally do these. What does this mean if you generally need to do very small modifications? It means that it's inefficient. If I'm just writing out an entire byte, I just overwrite it generally. I skip the read and I skip the modify. I just write it. I have new data, I overwrite it. If I have an entire 512 byte disk sector, which I need to overwrite in its entirety, I just write it out. If I can't do it in that size, if I have to modify a piece of it, I have to do a read and a modify and a write. That's twice as much I/O, right? Because I'm reading and writing instead of just writing, which means when you're writing a program and you want it to be efficient, whether it's on a disk or on a memory, you need to have some understanding of the granularity of the storage system, and it means you need to try to do operations in larger chunks than the smallest size of addressability. Make sense? Okay, that's tonight's free for you. That's tonight's performance lesson. What I'm going to eventually do is get sponsorship for these. So I'll be like, that's tonight's performance lesson brought to you by Google. This is not going to happen, actually. And when I do it, I'll spell lesson correctly. Okay, so brought to you by Google. Anyway, so that's a very small aside. But when I am talking about why did we get into this is because when I talk about memory, you should really have it in your mind that the physical memory is byte addressable. I can refer to any, physical memory is from 0 to whatever the max size of your physical memory is. How big is a physical memory today? How much memory is in your systems? A bunch. Could be a terabyte. Yeah, you can definitely have a terabyte of memory, which is unbelievable. Certainly 32 gigs, 64 gigs. You can get Amazon instances, right, of terabytes of memory on a single system. It's amazing. So that's a lot of physical memory, and you can address each byte. And if you want to refer to bits within those bytes, you have to do a read, modify, write. Or if you're just reading them, you just read it, of course. Okay, so we have our byte addressable memory. But we want it to be very large. And what we really want it to be is we want it to be that we have, say, process 1, and it has its address space, and process 2 has its address space. Oh, I did that outside. Sorry. And what we want it to be that, well, this is a virtual address space 1, virtual address space 1, this is virtual address space 2, and what we have over here is just what we'll call the physical memory of the system. We know that this is an illusion, that each process really doesn't have its own private memory to deal with, so somehow we have to place these address spaces or pieces of these address spaces, these virtual address spaces, in physical memory. And that's going to be our challenge of our virtual memory system. And we need to do that in a way that has a little bit of hardware support so that every time what we're going to do with address translation, our very basic mechanism, is what we're going to do is on every memory reference, we're going to translate the virtual memory reference or the virtual memory address from the process into a physical memory address where that data, whatever it is, resides. That's all we're going to do. In fact, everything we're going to talk about for the next few weeks relates basically to this mechanism of address translation, of turning virtual references, which the process thinks it's referring to its own private memory, into physical references. Very simple, virtual to physical translation. So let's start with a very simple mechanism. So mechanism number 1, introduced on the most ancient of supercomputers from years past, not really so much in use today, though actually, fascinatingly, this basic technique is receiving a revival for reasons that we'll come to understand in a few weeks when we see some of the problems with modern systems. And this technique is generally called either just dynamic relocation, or sometimes people call it base and bounds, because that's all it is. It adds 2 registers to each CPU that tell us something about how the relocation of your address space in memory is happening. So to understand that, it's also called base and bounds. So let's try to understand that just a tiny bit, and then we'll probably maybe we'll just get through this for today, and then we will take a break and then come back to later today. So let's understand this by having a simple example. Process 1 here has an address space, virtual address space. We'll call this address space 1, and has some stuff in it. Now we're going to assume at first, we're going to make some unrealistic assumptions. We're going to assume that this is really small, actually. We eventually want to build a very large virtual address space, but that turns out to be hard. So when things are hard, you reduce the problem, solve the simple problem, and then build up. So let's do that here. We'll have process 2 as well, and process 2 has its own private address space. It's also, we'll call that address space 2, and this is also small. They're small because what I want to be able to do is in my physical memory, I want these for now to be able to fit in their entirety in physical memory. That won't generally be possible. Eventually, we'll have many large virtual address spaces which have to share the same small physical memory. We're going to start with something more simple here. The way we're going to do that is simply we're going to place each address space. Oh, I should make these different colors because you know how excited that I get about that. Also because it will make it more clear. Who knew that something I'm interested in could also be useful? And what we're going to do is simply place these at different locations in our physical memory in entirety. So this is the entire red address space, of which we call address space 2, and the entire blue address space is being put into this earlier part of memory, and this is our real physical memory. Physical memory. And by the way, it's very important to keep track of what's an abstraction and what's real in this world. There is eventually something real. I mean, amazing thing about computer systems. We build all these completely made up things that are all just ones and zeros, right? There's so much, like a very complex piece of software, eventually just a bunch of ones and zeros, and represented by, voltages and things like that. But the physical memory, it's DRAM, it's some chips. You can touch those things. They are 100% real things in the sense of they are some things you can touch. Our abstraction of virtual memory, these address spaces, are just some sort of abstract. It's just an abstraction. It's just a way of thinking about how things are being presented to the user or the developer or whatever. So this is it. We're just going to place this address space here, the second address space down here. Now remember what's happening. I think these are going from, say, 0 to, I'll just say max for simplicity, and 0 to max over here. Each process is referring to, might have code loaded at address 10, and maybe at the end of the address space some kind of stack at high addresses. But they have to be translated. It's like 0 over here maybe has to translate to physical address 100, because that's where the first byte of address space 1 is loaded. Address space 2 maybe got loaded at address, say, 1000. Which means that when a 0 comes out of address space 2, the address translation mechanism has to turn that into 1000 before it goes to memory. If we don't do that translation, we are not going to get the values that we desire. That's all address translation is. Everything we talk about, that's all we're ever going to talk about, is taking the address that comes out of the process and somehow magically turning it into the correct address where the information, whether it's an instruction or whether it's data, resides in physical memory. How are we going to do this? Well, we have our friend, the CPU, represented here by this box. It's our CPU box. And what's great about the CPU box is we can draw inside of it, guess what? Another box. This is amazing. We have an ability to draw lots of boxes. And what we've learned from this is we can name the boxes. And the boxes here can be named the memory management unit. This interior box, called the MMU, is the part of the processor that helps us with address translation. Whatever we do with address translation, it's going to be inside of this MMU part of the processor, and the MMU part we're going to make increasingly sophisticated in order to provide us with better properties, performance, generality, etc., that we require from our virtual memory abstraction. So what's inside the MMU? Well, for this very basic technique, which I told you already was called dynamic relocation or base and bounds, as you may already know, we just have 2 registers. Now, remember this is 2 registers per CPU. If we were talking about a multi-CPU system, each CPU has its own memory management unit and it could have different values in those. But we're just going to talk about one CPU for now. Those 2 registers, as you probably already know and certainly could have guessed had you been playing along, are called the base and the bounds. And very simply, they represent very simple things. The base here represents the address in physical memory where the address space of the currently running process starts. So if we look at our picture here, the base value when process 1 is running, right? This is process 1, this is process 2. Oops. Process 2. The base value for process 1 is very simply address 100. The base value for process 2, which I wrote awkwardly over here, is simply 1,000. And what we generally know is what's going to happen then is when some sort of memory reference, and I'll say this very carefully, a virtual memory reference comes out of a running program, what is going to happen is it's going to go into this memory management unit. And simply what's going to happen is, so let's look at our MMU again, but this time using what's called a bigger box. What's going to come into it is a virtual address that the program generates. It's super important to remember this. If you remember nothing else from the virtual memory part of the class, every address that you ever see in a user program is a virtual address. You do not know where in physical memory this thing is. Every address, every instruction that you might have a function pointer, which is an instruction address. You might have a pointer to some data structure. You think you're a low-level hacker because you finally figured out pointers. It's just an illusion. You don't know where these pointers are pointing to. They live in physical memory in arbitrary locations determined by the masterful OS. That is the nature of the address translation. You, as a user programmer, only see virtual addresses, and they get translated constantly by the MMU to the actual location that they live in. This you must remember. The virtual address then comes into the MMU, and what happens is we have to generate a physical address, and that is what needs to come out of this, a physical address, and the physical address that comes out is what goes to memory, because memory is physical. You can't give a virtual memory address to a physical memory. It's not relevant. Hey, I'm accessing memory address 10,000 in my address space. Well, that's a virtual address. I need to know where it is in physical memory. I can't just go to 10,000. Every process has an address 10,000. They can't all map to the same location, generally. So how do I get a physical address? Well, it turns out to be very easy in this case. I take the base value, which is a physical address, and I essentially just add the virtual address, which you can think of as an offset. And that's how I get this thing. It's such a simple thing. You can see why this was the first mechanism people built. It's so simple. It's super fast. It's just an addition. And it gives you some rudimentary way of sharing memory, right? If we can fit the address spaces of like this address space and this address space, if we can fit them in physical memory, then this is a really great way to share physical memory. You're here, you're over here, and you all have your own little private memories. And each of you can generate address 10, and they're just mapped to completely different spots. If process 1 here generates address 10, where's it going to go? Physical address 110. Process 2 generates virtual address 10. Where's it going to go? Physical address 1010. The translation allows us to seemingly be accessing the same memory address, but really those are completely different physical addresses. Hopefully, kind of a review for everybody, hopefully. Any questions about this? Yeah. Yeah. Yeah, that's a great question. So that's absolutely true. The question is, on a modern OS, modern OS does allow actually sharing of memory between processes. And at some point that means, process 1 has its address space, and then it has some little chunk of that address space, which maybe process 2, maybe somewhere else, has mapped into its address space, maybe at a different location. And what that means is those little chunks actually refer to some part of physical memory that's the same. Dynamic relocation, which is our most basic way of building a memory management unit, doesn't really support sharing. So that's already one problem we have with dynamic relocation. And as we build more sophisticated machinery, we'll see how modern systems can support nice features like sharing. And sharing, of course, is really nice because it allows you to use less memory for the same amount of space. So long story short, we will do this later, but not that much later. Not later today, if you're worried. I mean, we could honestly just stay here all night and like do the whole class. We could do it in like 2 days, and at the end you would have learned nothing. But that's okay. So you could be saying, am I going to learn anything anyway? And then why not get it over with? Actually, there's this one college. Have you heard of this college? Colorado College, where you don't take 4 classes over a semester. Who's heard of this? Anybody heard of this? It's like you take one class for 4 weeks intensely, and then you switch to the next class, which also sounds like torture. I mean, we could barely get through 3 hours. So I don't know how they do it, but I'm kind of fascinated by it. Does anybody know anything about it, actually, other than I've heard of it? Did I make that up, by the way, or is that correct? That's correct, right? Okay, good. So now you know to trust me. All right, good. Lesson number 2 of tonight. You can trust me. Okay, sometimes. The key is knowing when to trust me. But when? Who knows? That's the open question. All right, let's actually just erase that. That seems wrong. You shouldn't trust me at all. Okay, that's lesson 3. Don't trust me. Okay, so we have our basic memory management unit, and it's pretty simple, but you've noticed we've left out a part of it. What part have we left out? The bounds. So what we've clearly learned is the bounds doesn't do anything. People built 2 registers, but they only needed 1. Isn't that crazy? Those people of the olden times did everything wrong. So what do we need a bounds for? Yeah. Yeah. The basis for translation. By the way, I'm sensing these lessons aren't going over as well as I'm hoping, so I'm going to have to work on that. Base is translation. It allows us to move a virtual address into wherever in physical memory. The bounds gives us protection. Because what it's going to allow us to do is check that we're within our address space. Now, depending on how we define these bounds, if I say these are all kind of like the same size address, I haven't said how we determine how big this address space is. But if they're a certain size and they can grow, the bounds are going to tell you how big they are at any given moment in time. So that's what the bounds are going to do. So if we think about our MMU, what we're doing is doing our base and our virtual address, and then we do a check. We check that it's within the bounds. So for example, our address space here might have a certain size. And the size might be, say, 1,000 bytes. Or, if we were thinking like computer people, we'd say 1024. Because there are actually good reasons that we refer to things in powers of 2, because we usually have so many bits that we can refer to make an address. And so if we have 10 bits, we can refer to 1024 bytes max. So our bounds gives us a protection check and a size, which is kind of interesting. Sorry that I keep scrolling back and forth. It's kind of interesting because what it means is we have to remember our abstract machine that we were building. Remember our abstract machine was, here's our CPU abstractly. And remember, all a CPU is a while one loop, right? If somebody ever asks you, what's a CPU? You say it's a while one loop. And then they look at you strangely, and they think you don't know anything about computers. So then you say, let me explain. And you say, what it's doing is it's doing a fetch of an instruction, program counter. Then it's figuring out what that instruction is. Then it's executing that instruction. And then it's repeating it. And you're like, boom, while loop, done. But, remember, always remember, in OS class, we place limits on things, right? We force you, for example, to, do lots of projects. We force you to do lots of things. But what we force you on the CPU to do is you cannot just execute any instruction that you want. Because if you could, we're not limiting your direct execution. We're just allowing unlimited direct execution. And unlimited direct execution is just the beginning of anarchy and chaos in the world. This is why Spectre and Meltdown were front page news, is because it's the beginning of anarchy in computer systems when you can not be checked and read any memory address that you want. That's bad. Amazing, that's still a problem today. So we have limits in here, and the limits on the MMU side in our simple system so far is our bounds register. And what that means is that when we have two options. If it's okay to access the memory that you presented to the system, then just go ahead. I'm going to flip back to this picture we had earlier, way back here. If we generate something between 0 and, say, 1,000, well, it's going to be translated to physical addresses between, or 0 and 999. It'll go between 100 and 100 plus 999, 1099. But if it's not okay, if the hardware checks it and says, you cannot execute this instruction, we have a problem. And if it's not okay, what we're going to do is we're going to raise an exception. This actually is getting us closer to understanding, at least let's say, the meltdown part of this famous processor bug. What happens in meltdown, how many people know enough about computer architecture to know what, say, pipelining is? Pipelining. What's pipelining? Somebody say. Yeah. Well, that's reordering. We don't even need reordering to do pipelining. Pipelining is even simpler than that. That's true too, yeah. Yeah, you can take like a bunch of it. What pipelining is in a processor is basically, to process an instruction, you have to do a whole bunch of stuff. Like you have to get some things register, some values from registers. Then you have to maybe add them together. Then maybe you do something. Then maybe you store it back to memory. So executing a single instruction takes a long time. So what modern CPUs do is they do this thing called pipelining, which basically first they'll work on the first bit of the first instruction. And as they're working on the second bit, which uses a different part of the CPU, they start working on the next instruction ahead of time. And then they work on the third bit of the first instruction, the second bit of the second instruction, and the first bit of the third instruction. And it continues like that. And that way you can use the CPU in hardware better because you're not just doing one instruction at a time, you're actually working on many at a time. Now, what's funny is that means that the first instruction that you might be doing might eventually you get to some point where what you're doing is you realize this instruction was illegal. It's going to raise an exception. And we're going to talk about what happens with an exception in a second. But what you've done, which is actually 100% at the core of this meltdown problem, which we will understand by the end of class, not today, at the end of the semester, what it means is you partially have executed some further instructions that should never have executed because the first instruction in the sequence is going to raise an exception. What that means is you've changed the state of the CPU a little bit with those later instructions that never should have executed. And it turns out that problem, which has been sitting there dormant in CPUs for at least 30 years, is a huge security vulnerability. It's fascinating. I find it so fascinating. You could have just stared at it, in 1985 and figured this out, and it took 30 years for people to figure out this is a problem. Anyway, this was what we call an even more random aside. So ignore this, or be fascinated by it, or be bored by it, or you weren't listening at all and you're wondering, what am I talking about right now? All of those are possible in the confines of B10 Ingram Hall. So anyway, where are we? We fetch, we decode, we execute, but we check, is something going wrong? And when something is not okay, what do? The hardware raises an exception. Illegal memory access. The hardware doesn't know what to do with that because it's just hardware. Hardware's pretty dumb. It just does things fast. It's good to have friends that do things quickly but are dumb. But you have to tell them what to do. Otherwise, they don't know what to do. In this case, we tell the hardware what to do all the time because we're the OS. That's good. We're smart. So what we're going to do here is very simple. The hardware is going to say, hey, OS, somebody did something wrong. This process that's running tried to access some memory that it shouldn't have, bad memory access. And then, of course, what we've done in the OS, well, what have we done? At the start, at boot time, remember what we did? The OS set up exception handlers, code that will run when bad things happen. And in this case, we're going to do something very simple. The OS will generally say, okay, the process that accessed that, that's a bad process, so I'm going to kill the process. And that's how that happens. Kill the process and move on. You access something illegally, I'm not going to let you execute. And like I said, fascinatingly, the way processors are implemented, because they don't just execute one at a time, is actually still a fundamental problem. Not one that we're going to worry about for a long time. Okay, so let's talk about what's good and bad about base and bounds, and then we'll take a break. Base and bounds is fast. It's simple. These are great properties, by the way. People undervalue the beauty of simplicity. If somebody says, people, in fact, this happens all the time with smart people, right? You're all smart people. You're in school. You try to dazzle your friends by telling them complicated things. But actually, it's very hard to build simple things. Complicated things are easy to build. It's often a sign of building something badly, right? When do I know that you're going wrong on one of the programs that you're writing? It's that it's too complicated. You're handling cases you shouldn't. You've made a program that has one general case and one exceptional case into 10 exceptional cases that are actually all the same case. That's complicated, but it's not good. We should value simplicity. So base and bounds is fast and simple. It's just an addition and a check, and it's very fast, and it's very simple. It's very easy to understand. But, so these are pluses. It has a lot of minuses. What are some minuses of sharing memory in this way? That just puts your address space into one contiguous part of physical memory. Yeah. What do you think is limited about it? It is limited, that's true. So it is limited, but what can we be more specific? What do you think? Oh, no, it's okay. I don't think there's any problem with that. Yeah.
If one process is given a very large portion of the physical memory space, but uses like memory, it can like on a large portion of the.
Yeah, we certainly have. I mean, one thing we have to do is, it's actually even hard to allocate memory. It's kind of almost what you're getting at. Because, why is it hard to allocate memory? Because you have to always find a large contiguous region, right? When a new process gets created, you have to find a huge chunk of memory where it's going to fit its entire address space. So that's not so great. It's hard to allocate. What else? Yeah. Similarly, it is hard to expand. Because when you have a physical memory and you have, say, address space 1 here, when it wants to grow, well, there might be another address space here. And that you have to worry about that. Of course, you can deal with that. You can move it, for example. The OS could do that. So we have some negatives. And of course, it's hard, as we talked about already, it's hard to share memory. We'd like to be able to share memory. When would we like to share memory? What are some really good examples of memory that we'd like to share and only keep in physical memory once, but put in the virtual address space of more than one process? What's a good example of that? Maybe somebody else. Yeah. Yeah, code, right? Code, absolutely. You run the same program, like you have multiple shells open. That's all the same code. Why would we keep many copies of that in physical memory? We just keep one copy, and we want to point multiple virtual parts of virtual address space to it. That's very hard to do when you only have this very simple base and bounds. So we have a lot of problems here. What we haven't talked about, which I'll talk about more, is we haven't really talked about all the OS involvement in this. We'll talk about that more later too. So that's base and bounds. It's an introduction to virtual memory. We're trying to build the full abstraction of virtualized CPU and memory together that's efficient but protected. We will continue to do so, but now we will take a break. Now we need something for our break. What do we need? We need our discuss with our friends. Question number 2 of the evening. What should we discuss? I Oh no, I haven't. I only thought of one. Sports themed movies. All right, best non-sports themed movie. So I've limited my. Now I'm going to have to really dig deeper next time. So something to consider over break.